Today we're going to continue our conversation with polynomials by actually switching gears a little bit and now focusing more on the graph of a polynomial. Now, you actually haven't really talked about the graph of a polynomial yet, although we've talked about graphs of other kinds of equations. The truth is this is a major idea in Algebra 2. I guess everything's a major idea in Algebra 2. Now, before we dig into the details, let's just kind of summarize that when we talk about a polynomial, we're talking about an equation. Of course, it's a special kind of equation. It's got exponents and it's got terms, but basically polynomials are equations. And in math, equations can all be graphed. Equations are graphs. Now, graphs visually describe patterns. They show us the patterns by the way they behave. Now, when we say behave, we don't necessarily mean like some kind of misbehavior. We're just talking about the way that they graph. Maybe they go up, maybe they go down, maybe they turn. You're going to be learning all of these things. Because polynomial graphs, they have some pretty unique behaviors. Again, they're going to twist. They're going to turn. There's actually all kinds of neat things that they do. Multiple times they will do this. Now, the comments here about a jigsaw activity, well, we're not going to be able to do that. Since you're watching this through a video, you're not going to be breaking up or meeting up with a home team. You're not going to be splitting out into expert groups, which it's kind of unfortunate. This is a neat activity to have you guys sort of go through, but we're still going to get the same learning. We're just not going to be doing it with the jigsaw activity. So when you're ready, let's continue. Let's actually analyze this polynomial graph. Now, this is a big deal. What you want to realize is that everything we're going to do in the next 20 minutes is all based on this graph. And it's a different kind of graph, isn't it? Yeah, it's not a parabola. It's not any of the graphs that we've looked at before. That's because it's a polynomial. It's got some unique behaviors. And what we want to do is we want to start to be an expert with each of these. Now, domain and range. Well, actually, that's not really a new idea, but it is something that we want to get good at again. Remember, domain is looking at the graph's left and right values. Of course, the range is looking at more of the graph's up and down values. Now, if we go to this graph, we can think about, first of all, the left to right. And what we'd want to do is definitely notice that the farthest we can go to the left, the farthest we can go to the right is each of these red dots. More specifically, we want to give the value, the place of these red dots. And you'll notice that what I'm doing is I'm giving the x value. That's because a domain is x values. So that's all I need to think about when it comes time to give the domain of this problem. It would be nice to write it in interval notation. It's just very simple to give the starting point -5 and the ending point 25. Now, when it comes to the range, the truth is I don't really want to be looking at all at these 2 points. No. I want to look at the furthest point to the top or the furthest point to the bottom. The truth is I want to be looking at like a whole different way. I want to be thinking about how far this graph goes down. And when I say that, I want to give the y value. Of course, the y value comes from the y-axis. This y value is probably a little easier to see up here. I'm pretty sure that it's going to be at 10. Yeah, it's going to be at 10. So, are you ready for the range? Okay, it's different from the domain. I look at the farthest the graph goes up and down. And I can see again that it went down to -15. That's more like a starting point. And it goes up to 10. Next, and just so you know, we're kind of looking at all kinds of different things with each of these, with this graph. So is what we're going to do next the same or related to the domain and range? It's not. It's just a whole different idea. We're going to look at a few good points. Now, really what I want you to understand is some good notation. Some good notation is to understand what f of 10 is really talking about. F of 10. You see, f of something, first of all, of something is an x value. So 10 is an x value. If I'm going to do f of 10, that's actually talking about a y value. So basically, we're trying to find the y value when x equals 10. Okay, wait a minute. The y value when x equals 10. If you go up to your graph, x equals 10 right here. And if I go to the graph when x equals 10 and look for the y value, then it looks like it's going to be something pretty close to -3. That means that when x equals 10, the y value at this point is -3. F of 10 is -3. Can you find some more? All you got to realize is that these are x values. So like 22, that's an x value. Okay, I'm just going to go up here. Whoops, I'm going to go up here to 22. And when I go down, of course, looking for the y value, now you got to understand that some of this can be an approximation. I mean, if I don't draw my line nice and straight, I might get something a little different than my neighbor. I feel like this is somewhere around y equals, what, -14, maybe -13. It's good. Let's just use -14. The main thing is that you want to realize that -14 is the y value, and that represents f of 22. F of 15. X equals 15. Sorry for all the moving around here, but when x equals 15, it looks like my y value is maybe over here more like at -11. So again, I get -11 when x equals 15. That means f of 15 is -11. You want to try a couple on your own? I mean, you really should. You should be able to find some of these spots. Remember, they're just x values. X equals -5. Y equals 5. X equals 8. X equals 8. Oh, wait, x equals 8. That's a y value right there. That y value right there is y equals 0. Okay, that's kind of special. And how about f of 0? Why is there like a star beside this? Well, remember, f of 0, that is when x equals 0, that's like a y-intercept. So x equals 0, y-intercept is 10. I'm going to slide back down here again. Sorry about that. So we have some notation. Yeah, f of 0, it's always referring to the y-intercept. F of 0 is always the y-intercept because x equals 0. Just something worth repeating. Can we do a little bit more notation? Can we add some stuff together? Sure, we can add together as long as you understand that you're just adding each of these y values. I feel like we already figured out that f of 22 is -14. I feel like we already figured out that f of 15 is -11. Again, we found those up here. So what am I doing now? I'm just adding these together. I'm just adding these y values, and I guess I had a little spot for that, but we end up with -25. Can we add a few more? f of 10 plus f of 8. Now, that's going to require you to find f of 10. F of 10, that means x equals 10. Oh, we already found that one. Okay, that's y equals negative 3. Okay, so that's just going to be like taking negative 3 plus, I think we already found f of 8, did we not? F of 8 is 0. So negative 3 plus 0, of course, that's just negative 3. How about f of 5 minus f of negative 5? I feel like I still need f of 5. Now remember, 5, that's the x value. F of 5 is the y value. So the y value there, I think it's 7. Let's say that it's 7. I mean, maybe it's closer to 6, but 7 works. Now this is like taking 7 minus, I think I already found this one, so minus 5, 7 minus 5, okay, that's just 2. Hold on a second here, something seems funny. Did we get f of negative 5 correct? Yeah, okay, yeah, nothing's funny. So we get 7 minus 5. How about something like this? Can I do a multiplication problem? Yeah, you can multiply. It's just going to be 3 times, now f of 20 just means x equals 20. So what's the y value in x equals 20? Way down here. And way down here, looks like it's something like negative 15. So f of 20 is negative 15. 3 times negative 15, well, that's negative 45. So some notation. Okay, let's keep going because each one of these is something special. Roots. Roots. What are roots? Well, roots are, maybe you remember from the last chapter, they are also called the zeros, or they're called the x-intercepts of a graph. So if I want to find the roots, I'm looking for the places where we have an x-intercept. X-intercept. Okay, that's an x-intercept right there. Now, how do I give the value of that x-intercept? By the x value, silly. X equals 8. So our graph has one root. It has one x-intercept at x equals 8. And yeah, I guess I wanted you to label it with an R, so we can call that spot the root, or label it with an R. Now, roots are special. Roots are special because the graph is going to equal 0 at a root, which means that f of x equals 0. That is, the y value equals 0 when x is a root. Now be careful here. We're simply saying that the graph is equal to 0, and quite honestly, that's the same thing as f of x equaling 0 because it's a y value of 0. And that always happens at a root. That always happens at a root. Positive and negative. Now I know you guys know what positive and negative means, but when we talk about the positive or negative part of the graph, we're actually talking about either the positive y values, that's the key, y values, or negative y values. Or the negative part of the graph would be negative y values. Now what I'd like to do is I'd like to switch the color that I used here, because quite honestly, usually I use red for negative, but I use blue for positive. So I'm going to switch that. That's just me. I'd like to show you the positive y values on this graph. Do you want to see them? The positive y values on this graph are the ones up here. Make sense? Positive y values, they're up here. They're in a positive place. They're above. I'd like to show you the negative y values now. The negative y values, they are below. They are down. We call those the negative y values. Let's change the color on this root. Let's make it black. Interesting. It seems like that the root is the place where this changes. That's exactly right. That's exactly right. Y values will only ever be able to change or switch from positive to negative. They'll only ever be able to switch from positive to negative when a graph passes through a root. Think about it. The root is the sort of the gate. It's like the point where it passes 0. Now, can we give some notation? F of x greater than 0. That means y is greater than 0. If that means y is greater than 0, then we're talking about the graph being positive. And f of x less than 0 means that y is less than 0. Well, that just means that the graph is negative. So what we're trying to say here is that we have kind of some notation to basically describe positive and negative. When you see f of x greater than 0, please don't panic. When you see that, you just want to say the graph, or you want to say the y values. So we say the graph or the y values are greater than 0. And for our graph, that is happening, like we said, that's happening everywhere in this blue region. Notice the way I'm going to give the sort of the address of this. It's everything between -5 and, well, between -5 and 8. You see, everything between -5 and 8 is blue, and so that means it's positive. Now, technically, if I equal the number 8, I'm going to equal 0. So I'm going to use a parenthesis there to signify that it's like a soft stop. How about f of x less than 0? F of x less than 0. That means the graph is less than 0. That means negative. Where's the graph negative? That's right, it's in this red region. Let's talk about the red region. Notice the red region starts at 8 and it ends at 25. Now, the other thing to notice is that I'm giving my answers as x values. That's correct. You always use x values to describe a position or a location. So my location starts at 8 and it travels to 25. Again, those are the x values for the red part of the graph. Are you still with me here? What's the difference in all this stuff? F of x equaling 0. That means the graph is equal to 0. The graph is equal to 0 at a root. F of x less than 0. That means the graph is less than 0. That means we're below. That means negative. And f of x greater than 0 means the graph is above, and that means positive. We have one more sort of section of problems to kind of be an expert with. Remember, normally you would have been learning this on your own, but today you get to kind of listen, and we certainly will be practicing this. But let's do one more. Let's do the extrema. Now, first of all, extrema, what the heck word is that? Well, it's actually a plural word that basically is talking about like extreme places. And extreme places are like maximums, and minimums. Maximums and minimums, I think I butchered that. There we go. Wait a minute. Now this has got me a little bit befuddled. Minimum. Something just looks awful here. Sometimes when you write something, it just doesn't look right. And of course it doesn't look right because it is supposed to be an I. So here we go, a minimum. No A's in that word. Anyway, extrema are maximums and minimums. Maximums and minimums of a graph. Relative maximums and minimums are going to be extrema, but they're going to be in like the neighborhood. They're going to be just kind of like looking in a certain location. But absolute maximums and minimums, now they absolutely will be the highest points on the graph. Let's see if we can understand absolute and relative maximum minimums for our graph. Now, I'm just going to use the image that's over here. You might want to flip your paper over since it's kind of small. I'm just going to use this so I don't have to keep flipping back between the pages. Negative 5, 5. Negative 5, 5. Well, it's right there. Do you realize that it is an extrema? Now, the way that I know it's an extrema is, well, maybe by thinking about if I was standing here. You see, if I was standing here, I would be standing and I would be looking up. That means I'm standing at a low point. We call that a minimum. But it's not the lowest point on the graph. No, it's not. You might notice that there's another point over here that's lower. That just means that negative 5, 5 is a relative minimum. It's a relative minimum. I'm just going to abbreviate the word min, not because I can't spell it, but just fits better. Now, it's a relative minimum because in the neighborhood of this graph, that's a low spot. But there's a lower spot, right? It's this guy. This is actually the lowest spot on the graph. It is the point 20, negative 15. Now, that point is absolutely the lowest point on the graph. If I was standing down there, obviously I'd be standing at the bottom. So we call that a absolute minimum. And let's add it into our little parenthesis here. I know the parenthesis is kind of small, but it's an absolute minimum. It is the lowest point on the graph. How about maximums? Maximums. Do you feel like that this point up here, 0, 10, is as a high point? You should. It's the highest point. If you're standing up there, you're at the top of the mountain. 0, 10. It's an absolute maximum. You're at the highest point on the graph. Now, there's one more. How do I know? Well, there's another blank to fill in, but it's this point out here. Now, this is an interesting point because if I was standing here, I would actually be looking down. Well, since I'm looking down, that means I'm standing at a high point. It's not the highest point, but it is a high point, which means it's a maximum, but it's not the highest point on the graph. It's not the highest. So, it's a relative maximum. Now, honestly, how do I know all these answers are right? Most of it's just visual. Visual. I'm just looking at the graph. I'm looking to see if I'm at a high point, a low point. There's nothing else fancy that I did here except I just looked at the graph. We will do more, but for now, those are called extrema. One more concept about polynomials. The concept of increasing and decreasing. Okay, I know this is a lot. We will continue to go over this tomorrow, but let's talk about increasing and decreasing. Increasing just means that the graph is going up. Or, I'm sorry, graphs go up and down, So hold on here. Graphs go up and down as you go along them from left to right. The point here is that you have to always travel left to right so you can correctly think about the graph going up and down. Okay? Now, this means that a graph is increasing. A graph is increasing when you're going up. And this means that the graph is decreasing when you're going down. Of course, you always have to go left to right. You always have to go left to right. Let's mark this graph with some arrows to show when we're going up, to show when we're going down. Now, stop right here. How do I know? Well, honestly, I'm just moving along the graph. Notice I'm moving along the graph from left to right. And as you move along the graph from left to right, you would be going up when it's blue, going down when it's red, and, well, it looks like I'm going to be going back up. Okay? Now, something interesting happened here. That is, I switched from going up and down or going down to up at the extrema. The extrema are always when a graph will switch from increasing, decreasing. This is a key idea. And of course, the extrema we just found in the previous set. Now, how do I say when the graph is increasing? Because I can color it, but I need to be able to say it. Well, you simply use, once again, the x values. You see, you always use the x values to give a position. And so very carefully, I say -5 to 0. Not 10, but to 0. So the graph is increasing from -5 to 0. Now, technically, it's going to be a parenthesis because if I get to 0, I'm at the very top. It's also increasing from 20 to 25. It's increasing from 20 to 25. That's the other blue section. Again, I'm going to use a parenthesis around 20 because if I am actually at the bottom, I'm not increasing or decreasing. How about the decreasing? The decreasing is this red space, and it starts at x equals 0, and it ends at x equals 20. So from 0 to 20, my graph is going down. It's decreasing. I'm actually going to use parentheses on both of those. Again, if I get to that point at the top or bottom, I'm not increasing or decreasing. Now, there's no homework tonight, okay? I just want you to take a breath, come back tomorrow. We will kind of talk about this a little bit more. Honestly, we will go over it. We take a couple days, give you a chance to learn these ideas. So what you see at the bottom here is not homework. It's actually what we'll be doing in class tomorrow.